Recording is rolling. It is Wednesday, March 18th. I have got all your papers back in your folders. Anything you turned in up to yesterday, graded back in your folders. If there's any recent quiz, want to do quiz correction, see that. Okay. Now, yesterday I was covering refraction with you guys. You guys remember we did refraction, ray diagrams. We're looking at lenses. There's a converging lens that can act as a magnifying glass. Right? You guys put together ray diagrams for that. Okay, and what makes this refraction work? Well, part of the process is that where does light move faster? Through a vacuum or through the glass? Yeah, through a vacuum. And through air, it's pretty close to the speed of light. Okay? And you can quantify how much light slows down. It's this ratio right here. Guys, here's the term. I mentioned this yesterday, but I never actually put it in print. But here it is in print. It's called index of refraction. You guys see index of refraction? That's what this N is right here. And it's the ratio of, guys, how do you read that ratio? What divided by what?
Speed of light divided by speed.
Yeah, speed of light in a vacuum, which is a universal constant. That's what C is. Divided by the speed of light inside the material. So guys, should this index of refraction be come out when you divide it out? Should it be more than one or less than one?
More than one.
Yeah, it's got to be more than one. Maybe it's like 1.2 or 1.4 or 1.5 or 1.6 or something like or 1.38 or okay. Because the speed of light through a vacuum is going to be faster. Okay. Now there's what's called Snell's law. Oh, okay. You guys see Snell's law right here? Do you guys spot this equation right here? So index of refraction 1 times sine of theta 1 equals index of refraction 2 sine theta 2. I'll show you guys a video demo. I'll do a little demo right here, but materials I got. Okay. So what I want you guys to find is I'm going to get you guys a glass piece. I might get you guys a triangle like this. I might get you guys a semicircle like this. I've got so many of these and so many of these. Okay. Maybe have some extra. You can give that kind of a small class here. You guys can pick your favorite. Which one you want? Do you want to find the index of refraction of this or index of refraction of this? Because there's some index of refraction. I think this is actually glass in my right hand, and this is some kind of plastic in my left hand, I think. Okay, something like that. Okay, and then we'll do a project except place. Okay. Right, so figure out what is the index of refraction, and furthermore, there's another aspect which I want you guys to find. So what's the critical angle? Okay, now one side of this left, so real small. Okay, you guys just got a chord page. You can solve this chord page. Okay, I got this set up so you can find the index of refraction of whatever glass piece. I'm showing a semicircle here, but you can also do this with a triangle. And on the other side is, well, notice the laser I have shining in the opposite direction. And I want you guys to determine what's the critical angle. Right, so I played you guys some video demos yesterday. I'm going to do a quick recap. So this you guys saw yesterday, but I'm going to remind you guys what this looks like. So here he's using, of course, the semicircle piece. Notice he's shining the light in the flat side, and it's refracting out the curved side. And what's really special about this semicircle is as long as you aim the light right at the center, which he is, in his right center, right, it only bends once. Right? It only changes direction once. That's going from the flat side on the air to the flat side on the glass. Right? Now, once it emerges from the center, the fact this is curved like a circle, it can only go straight from there on out. Right? Because look at these angles. Because which angle is increasing faster? The side on the angle on the side of the air or the angle on the side of the glass? Yeah, on the side of the air, that's a bigger angle, isn't it? Right? And how are we measuring the angle with respect to what line?
Normal.
The normal line. It's kind of hard, tiny font here, but it says normal. That means perpendicular, doesn't it? Isn't that perpendicular to this interface between the air and the glass? It's perpendicular, right? So we got to do all that. Now, this next one, I think I should you guys do. He shines in the laser the other direction. What if he shines it in the curved side? Now he's still aiming for that central node, right? He's going to shine in the curved side. So it's really the same thing, just backwards, right? But there's something you can get experimentally from this kind of quickly. Right? That okay, I see the side on the air is that angle from the normal is growing faster than the side of glass. Right? But at some point, it gets too big. It goes to 90 degrees. Bam, right there. I just paused it right at that point. I see it. This went like flush 90 degrees. Now there's some reflection. That's not refraction. That's reflections here. Right? But the refraction went exactly to 90 degrees. Hey guys, what angle is left over on the side of the glass? What angle is that?
45.
Close. Yes, between 40 and 40. Yeah, I would say closer to 42. It's 40 something, right? That's the critical angle. And actually, if I go back to the original one I was showing you guys and I zoom right towards the end, where this angle is getting 80 and it's about to be 85 degrees, and then it cuts the video. Look at this refracting on the side of glass. It's the same angle. You see it? It's getting really weak at this point. He's gonna set it. It's getting really weak, but it's perfect. You guys see that same angle? Right? Now you can also determine that angle mathematically from Snell's law. which is this right here. Oh, and I was meant to show you guys my posters too. Okay, so here's Snell's law poster. Here's index of refraction down here. Okay, boom, boom. Right, so you guys got all that. Right, poster versions. Okay, and then I think you guys should have thumbnails of all these. Okay, and then there's this total internal reflection, where if you go past this critical angle, oh look, this critical angle lines up with this refracting at 90 degrees. Ah, okay. Here's the fisherman trying to see this fish, okay, and then but anything beyond that is just gonna internally reflect. Okay, good. So how would I do this? Here, I'll try the triangle piece. All right, I'll get you guys a laser in your hand. Hey guys, when I get you guys the laser, is this a dangerous piece of equipment? Yeah. Do you want to shine this in each other's eyes?
Yes.
Let's go with no. The answer was no. Guys, this can cause real damage to your eyes, so in your friend's eyes. So don't do that. So everybody knows not to aim the laser in each other's eyes. You guys know that? All right. So what I would do is, let's see. I'm going to trace this out. All right. If you get a triangle, you do triangle. Get semicircle, you can figure that out. Okay. And well, I need to measure off. I want to try in this laser. Let me show you guys what this kind of looks like. Okay, this laser light. Okay. And it only shows up so well on camera, but in person, maybe it's easier to follow the path of light. Ooh, see someone's like reflection or refraction and like the lights bouncing around. You know what? Let me get a different laser too, just in case it shows up better on camera. That any better? Yeah, I think it's a little better on camera. Maybe I'll just use this one. Okay, so I need to get a normal line, and you guys each have a protractor. So here, let's say I aim the laser at this point right here, and I'm going to measure 90 degrees from that point. There's 90 degrees, and sketch off a normal line. Right, and put my triangle piece back in place, and then aim the laser straight at that point. And I need to follow the path of the laser light. Oops. Okay, so in the speed of light this way, and okay, so it's coming in kind of this angle, right there. Okay, and then I see it refracting out. I think like over here. Okay, yep. I don't. Okay, I'm really focused. Actually, it's closer to here. I think. Okay, I'm really focused on what I'm looking at here. So I don't know how well it's going to show up on the video. Okay, but internally, this must have refracted this way. So like this. Okay. And actually, that does look consistent with what you guys saw in the video demo too. Okay. Which is that on the side where it travels faster, like the air side, this angle should be bigger, and the side where it's traveling slower, like the glass, it should be a little slower. Okay. So I want to compare what is this angle and what is this angle, and they're different angles. Okay. Now I can extrapolate. Okay. So just to be able to measure the angle with a protractor, because the protractor is so big. Okay. So I'm going to extrapolate a bit here. On the line. Okay. So here's the angle on the side of the air, and here's the angle on the side of the glass. Okay. So grab those angles and see how I would record that. I got a table I can record those angles. Okay. So if you guys remember how to use a protractor, I'm going to take this node of this protractor, I'm going to park it right on that central point right there, zero out the normal line, and measure the laser line. Now here is this reading, looks like 24 degrees. This is 24 degrees. Now on the side of the glass, that's going to be, let's see, zero that out, right there. Looks like 13 degrees. This is 13 degrees. So I'll go to my table. Let's say incident side of air, call it 24 degrees, and refracted side of glass, 13 degrees. Okay. Now, if you know that Snell's law, n1 sine theta 1 equals n2 sine theta 2. Okay. Didn't I just get the angles? I just measured the angles with the protractor. Isn't that right there? Bam. Right there. Bam. So I have those two, right? Okay. Here's one more detail, and then you can use a little bit of math and solve this. Okay. Guys, what do you think is approximately the index of refraction of air? 1. It is 1. Yeah. So, guys, for the index of refraction of air, just use 1. Just use that. Okay. For a perfect vacuum, it's exactly 1. For air, it's very, very, very close to 1. So we'll just call it 1. Okay. Okay. Now, do you guys see that you know everything at this point except for this M2? well, make sure your calculator's in degrees and not radians. Okay, can you guys check that too? Because the protractor's in degrees, so is your calculator in degrees? Okay. Okay, you should get an index of refraction of, well, I'll see what you guys get. Okay. If you're not sure you're doing it right, then let me go. Okay. Now, okay, are you guys okay so far? Okay, I don't want to do too much for you guys, but I want to do enough demo where you can see what's going on. Now, if you flip over the page, there's a, well, actually, I recorded the wrong side there. This is 24 degrees, 13 degrees, and so on. On the other side, there's a different question. It says, what is the critical angle? Now, you can determine the critical angle experimentally, which is to say, let me try to kind of do that with you guys here. Or you can get it, or you can calculate it through Snell's law after you know the index of refraction. Because here's how you get this experimentally. Right, so I can aim my laser light here. I can keep changing the angle. Guys, what if I change this angle on the side of the air all the way to like 89 degrees? If I could follow the beat of light refracted after that, that would exactly be the critical angle, wouldn't it? Or pretty close. As long as this angle is like 89 degrees, let's get close to 90 degrees. Okay, if I can see where it refracts on the inside, that's how you can determine that experimentally. And you guys saw in the video how to do that with this, which might be even more straightforward. Okay, or let me show you guys how you can calculate the critical angle, and it should be about the same thing, no matter how you approach it. Let's go to Snell's law. Okay, what angle did I just say would correspond to find the critical angle over here? What's the angle on the side of the air? Yeah, 90 degrees. Right, so I'll do N1. Which is just 1, isn't it? So maybe I should say 1. 1 on the side of the air times sine of 90 degrees equals. Okay. Now, after you find the index of refraction of glass piece, can you just go ahead and pop it in right here? Okay, so I'll write N2. I'm going to point to it and say no, because you would have gotten it within about 20 minutes probably. Okay, sine, and then to finish this out, this would be the critical angle, and then you can solve for this. You can solve. Okay. But mathematically, you need to do something tricky that we don't do too often here, but I think we did a long time ago. I think maybe is what's one of the algebra, what's maybe probably the last algebra step you need if you want to solve this algebraically. How do you extract an angle out of a sine? Inverse sine, inverse sine. So I'm going to do dot, 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 because I'm skipping some algebra steps. But the last algebra step is inverse sine of something. And that will tell you the critical angle. So you can solve for it mathematically. Okay? And do you guys remember how to find inverse sine using the calculator? You hit what?
1.
Second sine. Guys, if you hit second sine, notice that doesn't say sine. That says sine and then with the -1. That's inverse sine. Or arc sine. Okay? You guys remember that? Okay. All right. Well,
Nice.
I'm going to get all these materials in your hands. So I'm going to walk around, get you guys some lasers. Yeah, close down this video and you guys can do this lab. And I'll help you out. Turn this lab into a great trade by the end of class.